Cast is now starting. All attendees are in listen-only mode.
Well, welcome back, JR, and welcome back to most of the attendees. Also, welcome to anyone just joining us. It's great to have you all here. This is Solar Photovoltaic Project Design and Development Part 2. As I said yesterday, I thought the program has been going great so far, and hopefully the students agree. And I'm also looking forward to another good day here. As was the case yesterday, there are a few things that we must go over before we start. Remember everyone to please be logged into the webinar through your own connection. This is so that Halfmoon or you can prove your attendance if audited. Also, it's the only way for you to gain access to the quiz at the end of the program, which is a requirement if you're trying to obtain your continuing ed credits. Next, I want to point out that within the panel that is to the right of your screen, there is a section labeled questions. You can open this up by clicking on it, and then you'll be able to submit any questions you might have for myself or the speaker, and we will be answering those as soon as we can. For anything else that might come up, please call Halfmoon's customer service at 715-835-5900, and I'll be posting that number for everyone once again in the chat section. And with all that being said, I'm happy to begin the series once more. Please welcome J.R. Cromer.
All right, welcome back, everyone. We're about halfway through the program, and this is the halfway point, so we need to keep the pace going. Just continuing our design discussion, we were starting to talk about racking yesterday, and we're going to continue that discussion as well as talk about some balance of system strategy. So we were talking about yesterday the real tricky bit with particularly standing seam metal rooftops where you're clamping onto the seam rather than screwing through the metal. And, homeowners, they want to clamp onto the seam. My preference is to screw into the metal because, I've actually done it, and you shouldn't be afraid of making a roof penetration. Many things penetrate the roof. But the concern with the standing seam metal system is that you're not clamping on to every single metal panel. That if you skip over a metal panel, you're now putting a lot more uplift load on. You're doubling the uplift load on the next panel over, and it's not rated for that. So it's crazy how sometimes extreme wind can pick up a flat plate that's on top of a rooftop. So you want to make sure you're not unduly ripping off the rooftop by kind of overkilling the attachment points. Now, when I'm doing standing seam, yes, I'm clipping onto every panel. Sometimes these panels are sufficiently long that you don't necessarily need to overkill it too much, but certainly on the edges of the rooftop and along the top and along the bottom, going with way more attachment points than you think is appropriate is fine, and then you can start, staggering them out a little bit. Because, of course, when you're, the reason why installers don't want to attach every seam is when you're doubling the amount of clamps that you're buying, that's doubling the cost of your racking budget. So, installers are not really used to thinking about things in terms of over-engineering and designing for local wind code, even though perhaps they should. As design engineers, we need to be more cognizant of these issues. And so making the roof transition has never been easier. And in fact, it's so easy to take the cables from a solar array and put them directly into the attic that I think that should be the goal of 90% of rooftop solar should transition into the roof for an internal conduit run. The rooftop is not a place where anything should be. It is hot, it is cold, it is wet, and it's difficult to access. So, Why have an external conduit run exposed to the elements when you can go into a better protected, more accessible place? And the reason is people are afraid of putting a hole in their rooftop. Of course, chimneys, plumbing vents, gas vents, even satellite mounts. Even the shingles themselves have nails that go into the rooftop. So we shouldn't be afraid of putting a hole in the roof if you can do it correctly. And so the easiest way to do it correctly in the solar industry is to buy a specialty box for making that transition. And just the shell of this box with the little DIN rail for the mounting strip and the ground lug and the case, but none of the breakers or anything inside of it, which you may or may not need. But just the shell is around $90. So I can see why someone might not want to buy the box up front, but then if they go to their local supply house or say Home Depot or Menards or Lowe's, they're not going to find a 90C high temperature rated outdoor box that is easy to flash. I mean, I suppose, what roofers do is they get kind of plumbing boots to stub up the pipes. The problem with solar conduit compared to most plumbing vents is that it's much smaller than, your typical vent stack. And so the plumbing pipe boots that you can find at your local hardware store are really too small for the size of the hole that you're going into. So this box is a real popular way to do it. It comes with some flashing to get up under the shingles, and then you come into the box with your solar cable, and then you go out of the box down to your home run circuit, back to the inverter. So we're going to be talking about that home run circuit in the slides to come. And here's an example of a Spanish tile replacement, whether it be a pipe boot or a standoff. There's now you're replacing the entire tile as opposed to snaking a bracket through the tile, which is what we used to do back in the day. But then again, if you are doing a do-it-yourself project, taking the time to walk around the hardware store, you can find pipe boots, you can find outdoor rated bends, provided that you're checking your wire size. The conflict you'll get into when trying to kind of do it yourself off of standard parts for the roof transition is that this box becomes pretty high off of that roof deck, and that height from the top of this box to the bottom of the roof can sometimes be greater than the space underneath the solar array between the roof and the solar panels. So that can complicate the conduit run on some roofs. But also, I like to hide this stuff. I like to hide this box. I like to hide whatever this is underneath the solar array, at a corner of the array. Preferably the most accessible corner of the solar array is where this box would be, and you hide it underneath so that visually it looks really good, and it's really not that hard to unclip one solar panel from the rooftop. And to be perfectly honest, that box up on that roof can use the sun protection and weather protection by being hidden, and it is code compliant to put these transition boxes underneath the solar array. The only reason why you wouldn't put it at the very bottom of the rooftop is sometimes inside the attic, the very bottom of the rooftop is the most difficult part of the attic to access because of the roof slope. So putting it further up can make the transition from the roof into the attic a little bit easier to install. So what about this transition into the roof? There's solar cable, and it's literally called PV cable. There's solar cable, and what solar cable is just very industrial, outdoor rated, super thick, high voltage cable jacket. rated for direct burial, rated for outside of conduit. In fact, can be a little tricky if you want to put it inside of conduit because it takes up a lot, the jacket itself takes up more space than your standard cable of equivalent wire gauge. But it's more expensive than your THWN2 cable too. It's a high-end premium cable, commonly copper. And again, this is normally number 10. Let's say you wanted to transition into a bigger wire size for a very long home run circuit, or let's say you wanted to transition into cheaper THWN2 and go inside the attic, or potentially even THWN, THHN. I always use THWN, which is a wet rated cable. Sometimes it's cross-listed as both, sometimes it's not, especially when you buy from a supply house, you have to check. But the THHN is standard indoor electrical wire. It's not wet rated. And so the outside of this box on the rooftop is a wet environment. And so if you're running THHN all the way up to this box, that gets into a pretty gray area of code, which I just avoid by using THWN2 all the way home and through. For the actual cable itself that goes, you're like, okay, so now there's some conduit on the other side of this that the cable's running through. Depending on your inverter selection, if it's an AC run, like if you're using microinverters, this run could actually be done in Romex. It does not need to be inside conduit. Only DC needs to be inside conduit. So the actual rule is that DC feeder circuits for solar need to be inside a metal raceway for inside the building runs. So when your solar wires transition from the roof to inside the building, they need to go into a metal raceway. And why is that? Well, for one, it's DC discrimination. There is absolutely no difference between DC being required to be in metal and AC being required to be in metal. So, if this rule applies to DC, it should also apply to AC, and it doesn't. Your Romex feeder circuits can be outside of a metal raceway. So why is it metal? It's not for grounding. The metal's not there for grounding. The metal is there for physical protection. And so I suppose the justification for the metal clad requirement is, if contractors are driving nails through the walls to give it some protection, if rodents are chewing up wires, to give it some protection. These are all good things. They're not perfect things because, a contractor's nail gun, can go through metal conduit. So, in certain heavily regulated areas like New York City and multi-story, buildings, you might get requirements to say not just metal conduit, but intermediary metal conduit or rigid metal conduit. And depending on the building, maybe that's justifiable. And so perhaps the protection requirement for DC is coming from the fact that, really it's, electricians have been doing AC for a very long time and DC is relatively new. So, code is erring on the side of safety by putting this stuff into DC. In other countries, like in Australia, they don't have quite the same requirement. At any rate, those are the rules. So what I have found to be the easiest way to do a really nice looking internal conduit run is this. I'll use metal clad cable, which is different than if this metal raceway was provided without the cable inside it. If it's provided without the cable inside it, it's very, very difficult to pull cable through it. And so those kinds of cables are really only used for short custom runs made on site. This is pre-packaged stuff, and it's expensive for sure. But the metal coiling is wrapped around the cable, and that gives it better bendability. It lets it, run through the attic with relative ease. And I will just shove this out that hole in the roof and then run it all the way through the house and then shove it down the soffit of the other side of the building, wherever the battery inverter is going to come out with, and then strap it up to the rafters, and it's done. It's super fast, super easy. Costs an arm and a leg, but in terms of quality for having the array be installed with a high level of workmanship and time saving, it's often worth the extra cost. There's a couple of tricks that I use with it. The first is to be aware that your jurisdiction might be one of those that requires IMC or rigid, and that's generally for apartment buildings where hundreds of people live inside. It's only rated for damp, not wet locations. And so I would say the inside of that box up on the rooftop is a damp location rather than a wet one. Underneath a porch where it's sheltered from the rain, that's a damp location, even though it's outside. So, wet locations are on the side of a building. It's exposed to rain. So this cable is not rated for anywhere on a building except perhaps, other than inside it, except for areas where it's covered. And so I will take that to run this a few inches out the bottom of the soffit into a box. And then you can transition the rest of the run, strip off the metal and transition the rest of the run in, a very easy to bend EMT conduit run. Makes it all look nice and professional. When I'm selecting this cable, I'm actually going to upsize to number 6. And that's something that I do differently than most installers who will do, number 10, or maybe upsize because a voltage drop to number 8 is not uncommon. Going from number 8 to number 6, the voltage drop savings start to be like, it's not really worth it. But the reason why I go with number 6 is because this stuff standard comes with an undersized ground. And if you get the number 8 ground, that qualifies as the required ground going from the side of the building up to the solar array. And so instead of worrying about my conductor sizing, for voltage drop or ampacity, I'm spending way more money on this thing, and I'm not going to have any voltage drop, at all, because my conductors are well oversized. But I also don't need to run an additional ground wire. So all of my wires are wrapped up in the same bundle. That's how to do it in a code compliant manner. And then your ground and all your power cables are run up to the rooftop. At least for DC systems, where you would have a positive, a negative, and a ground. On AC systems, where you have 2 legs of power and a neutral and a ground, it doesn't matter. You're using Romex. You don't have to be in this metal stuff. But if I have 2 solar circuits going up to the roof, I'll get a 6-4 bundle, which is 4 number 6s with a ground. So if I have a 2-circuit array, I'll get the 6-4. If I have a 1-circuit array, I'll get a 6-2. If I have different sub-arrays where there's a section on one side of the roof and a section on another side of the roof, the jumper cable between the roof sections will be this 6-2, because there'll be 1 circuit, going between the 2 sub-array sections. So this MC cable is readily available. You got to order it in advance, but it's out there, and it really speeds up the install. And the fewer splices you can have, like if you can transition from NC cable into a conduit without a box, more power to you. It can work out that way with the right planning. Although most electricians have no problem mounting a box on the wall and transitioning inside the box. There are certain rules, whether or not you use a metal box or a plastic box, and technically inside the building it needs to be a metal box if it's DC. So you can trip yourself up just with the box selection. There is a specialty cable gland in the solar industry. Generally, you have to buy these things online from solar distributors. There are similar things that you can find at, say, Home Depot, but they're not the same. The solar cable is a little bit wider than normal, and so it really wants a cable gland that is specifically rated for PV wire. And you can go and look up the millimeter thicknesses and stuff like this on wire cable specification sheets. But this is something that's designed to, go at the end of a conduit run and have the cables come out of it. And while it is nice and neat, it's not the most code compliant way to do things by putting it onto conduit. Generally, you're putting this on the side of a box and feeding things through the box. Now, I will do a short stub of conduit out of a box, but the problem is there's no real, if you put this on the end of a piece of conduit, like right here, there's really no easy way to ground that conduit. You'd also have to, find some sort of grounding bushing that you could put behind it to ground the other side of that conduit to whatever, to the solar array or where. But technically both sides of your conduit need to be grounded. Now, for that matter, on a residential rooftop, if you want to stub out some conduit from a box to get to underneath the array to form this transition, that would be a reason to use plastic conduit instead of metal. Plastic is punier than metal, but sometimes for short, stubby runs, that insulated nature of the plastic can be an asset. And so when planning a solar project to reduce the time spent on site and reduce the time spent on the rooftop, the internal conduit run reduces the time spent on a roof. And you can even buy the cable pre-bundled so you can just shove it on up in there and get on with the project. On the ground, certain lengths of rails and like the optimizer boxes as well can be pre-assembled. I'd say this is an optional step, but I like doing it. As far as making the connections, these connectors are called Mc4 connectors. It's a multi-contact version 4 connector. There's a manufacturer who named them. They're the Mc4 company. Ironically, they opened up their standard for everyone to make, and now there's actually a variety of Mc4 connectors on the market. So you really have to make sure you're kind of using the same connector is the best practice. Then there's 1,000-volt connectors for commercials versus 600 for residential. But for the most part, while you want to use the same connector throughout the system, they'll all plug up to your solar panel. So just don't go buy a pack of 100 Mc4 connectors for a project and then go buy another 100 pack from a different brand. Stick within the brand. There are some quality differences in your connectors, and it's a common failure point because it is a field-made connection. That'll fail more frequently than like a machine-made connector coming from the factory. And so it's not the best idea to cheap out on the MC4 connectors. They cost $1 to $2 each. And so the way these Mc4 connectors are made is there's a little metal sheath that goes around the cable, and there's a special crimping tool that you can use. And the crimping tools, there's like hobbyist level tools that cost $25, and then there's pro grade tools that cost $400. And the main difference is the pro grade tool lasts longer and doesn't fall apart, and you'll be reusing it every day in the field. Get the better one. But if you're a do-it-yourself homeowner, the getting an Mc4 crimper is a lot better than trying to engineer your own solution. You want these leads to really clamp down onto that metal. If they don't clamp down, if they begin to slip, that is the common arc fault point, where you'll get an arc fault between this connector and this cable. In fact, I have found that just if this cable itself is not tightened up enough, you can start getting arc faults. And so it's important that you don't just have anybody making these Mc4 connectors. I mean, it should be an electrician. It's a common failure point. It definitely needs to be someone who is doing a good job with each and every single one of them. It's an important part. And whenever I have a failure, that is where I'm looking first. And if it's not an Mc4 error, that's when I actually have to start thinking about what it might be. So we talked about reinforcing the footings at the wind. Another reason to reinforce the bottom row is that's where most of the force gets when the whole array is covered in snow. And so in areas of particularly heavy snow, like around the Great Lakes region, I've seen pictures of solar where you only have the footing spaced out 6 feet or 8 feet, crushing through the deck of the roof under the weight of particularly heavy snow. So this was a design that came to me from a developer, and this particular developer was let's just say the customers were running out of budget before they were filling up the entire rooftop with solar power. And so in this particular project, the solar array was only covering a portion of the roof, and this is the design, the layout they came to me with. And it's like, well, there are a few things wrong with this design. First is we have subarray sections when we don't need them. And with each subarray, you're either going to have an internal conduit run between subarrays, and that's really not a big deal. I mean, it's getting another one of those transition boxes and doing an Mc4 run. But many installers will, run conduit between the two subarray sections, and it's just an eyesore. It's not as pretty as it could be. I also felt like they didn't really consider the shading impact. In this array, south is like off in this direction. And I don't feel like they really considered the shade on this dormer. A note of one thing that was interesting about their document is they specified a worst case tributary area. And that made me think about, well, what happens when rainwater lands on a solar array? It'll accumulate here, and then waterfall, and then waterfall. And yes, some will get through these cracks, but also some of it will accumulate, and that's why they're spelling out the worst case tributary area. And it's like, wow, that's really interesting, because I could see over 25 years when you take this much section of a rooftop and you dump the rainwater all along one thin strip, that's where the erosion on the shingles is going to be. And so for that reason, like it's actually nice to start the array down towards the bottom, although it's a trade-off between that and accessibility. So, if you don't start at the very bottom of the roof, you're not crazy for giving yourself some space, but think about long-term impacts on the shingles. Maybe it's easier to replace just the bottom line of shingles than the others, and so maybe you go in with the knowledge of the shingle. If your water is landing on the shingle, that's going to be your little sacrificial area. It's just worth thinking about. And then they had this long, ugly conduit run along the side of the rooftop. Well, furthermore, the roof, this upper section of the roof, was actually at a different tilt than the lower section, so their remote design was no good to begin with. I guess we could have started the array and split the difference and had it not be, a very dramatic error. But inside this building, they have elevated ceilings, wood ceilings that pretty much go straight from the roof into this cabin. And so with really long lag screws, you could get into poking through the roof of their self-built, really beautiful on the inside log cabin, and it wouldn't work good. So, using the same number of panels, we got away from the dormers and made it a continuous, symmetrical array, kind of gave the roof a smile, and then ended at the end with an internal conduit run into some attic space below, and it just made the array look a lot better than something that was just kind of thrown up there. Just keep in mind that from commercial code yesterday, we learned every 150 feet you need a walkway. A better rule of thumb and kind of what the racking manufacturers get into is about every 120 feet you need a break or at least an expansion fitting. So here's some kind of innovative racking systems. Maybe we should talk about the non-innovative racking systems first, but here we are nonetheless. This is a floating solar array, and this is where floating solar makes sense to me. There was a lot of, some Florida Power and Light or someone is doing a floating solar array by their oceanside airport. Japan looks at floating solar in the ocean. But the real value in floating solar is you might have free real estate at a heavy power load for a drain water storage treatment center. Putting a cap on top of the reservoir has benefits, but it's too expensive to do to get those benefits for the most part. But if you did cap the reservoir, you would get less evaporation, you would get less sunlight, so you get less algae. There's benefits to having a shade structure on top of these ponds. And so I guess if the project just had like break even cash flow proposition, you could always say, well, there's other benefits too. But the main thing is now you have the real estate for a nice large solar array to power the energy needs of the water treatment facility. And National Electric Code covers floating structures, so there is racking and material available for floating solar. I think it's an interesting concept. more widespread than what I would imagine, which I'd say no one would do that as opposed to rooftop or ground mount solar, but it does in fact, have there's projects already on the market with that stuff. In a minute, we're going to talk about commercial ballasted racking systems. Here's one that is made out of a plastic. And that's interesting to me because if you combined it with a frameless solar module, you'd literally be getting rid of all the metal parts of that system. In fact, that is one of the ways to get out of the rapid shutdown requirements, which I think is also an oversight. I don't, the danger with rapid shutdown is high voltage when the building's burning down. And if the building's burning down, there's the electricity is going to be going into the metal of the building. But at any rate, what this is really designed for is landfills. Because if you can put a metal-free panel, and this has a framed version as well, but you put a frameless solar panel on a plastic, tray and use it to cover a landfill, there's not going to be the corrosion from the off-gassing of the landfill. And then I also see sometimes installers using this kind of setup on the ground just to throw out a really cheap and potentially removable solar ground mount for temporary power, which is another unique application of this type of stackable modular racking. What I would notice is we've only been talking about rails being underneath the racking so far, with the exception of that one railless system we saw up on the rooftop. These kind of tray systems are railless commonly, and that can be problematic because it gets really hard for cable management. So, again, on a commercial ballast system, you're often bid these trays, and then the cost of, you think, wow, that's a really cheap racking system, and then the cost of the cable management just gets pushed on down the road. Either the contractor will bid for it or they won't bid for it, and there could be an issue with the contractor driving the design rather than the designer. Here's a system for a field where it's above the ground concrete pours. Why would you do that? Well, pile driving is the standard solution, whether it be a tracking ground mount or otherwise utility scale ground mount, they'll do pile driving. For anything smaller, more often you'll be renting an auger and drilling out the ground and doing a concrete pour. Here they've elected to do above the ground concrete, and I would suspect it's because the soil underneath is rocky. When I say rather, we know we're going to have problems whether or not we auger into the ground or we drive piles, so we're going to avoid them by doing an above ground concrete pour. I'm looking at some temporary facilities designs for a 100-person off-grid diesel-powered camp, and I'm looking at maybe using water tanks as temporary ballasts. And so now we're moving towards like commercial flat rooftops. And so there are very cheap and quick systems that, you just put the modules on, you weight the trays down with concrete. This particular one on the right, this manufacturer is very proud of how stackable the racking is, where they, normally racking delivery is a big giant ordeal, and they can deliver a racking system with a smaller footprint as far as shipping goes. And I can see how on some job sites that alone is what, what would get you over the limit. Like if you're shipping a racking system to Jamaica or whatever. Or if you're, I don't know, if you don't want to rent lift equipment very long, very long. But the problem with this kind of system is, from module to module to module to module, you're still having to plug the solar panels into each other and potentially mount microinverters or DC optimizers underneath. And on more expensive racking systems, you get pathways for that. We're going to come back to commercial racking in a minute. So tracking arrays. Is tracking worthwhile? The answer is yes, but at scale. And so, actually when I got started in solar 10 years ago, it was much easier to buy a residential tracking system then than it is today. Back then the solar panels cost 10 times as much as it is today. So today you have to weigh the option of just buying more solar panels instead of spending the money on a tracking system. But does that mean tracking is not cost effective? I would say that tracking is not a big enough market for residential to get any attention. If you look at the parts involved on a tracker, it actually can make sense. You're getting a boost in production for a similar increase in project costs. But why would a utility scale tracking company even consider a residential size project? In fact, it's been the opposite way. The residential tracking companies have now become the utility scale tracking companies, and they're not looking back. So I don't think you're crazy for thinking about tracking at the residential level, but as a profession, it's really non-existent at the residential level, outside of like statement pieces. But at the utility scale level, tracking will take that ratio, and we can see this in PV watts, and boost performance by 20 to 30%. And so the increase in cost to go from a non-tracking system to a tracking system does not cost the project, 20 to 30% more. It's less than that. And so it is cost effective to add tracking to a utility scale project. And most utility scale projects are tracking projects, at least by installed capacity. So, residential system, residential ground mounts, it's easier to keep things simple and have them be fixed in place. But by the time you get up to scale, the economics say, no, tracking is so much more cost effective that we have to do it when we're talking about installing a whole bunch of panels. The reason why we don't see commercial trackers and residential trackers, though, is more a lack of interest by the manufacturer than anything else. So these are different ground mount components that you would use on a residential system where you're not driving piles. For rocky terrains, there are ground screws that have a smaller footprint and can kind of, depending on your rock, if you have small rocks, they can kind of push them out of the way. If you have big boulders, hey, you're going above ground. If you have, nice sandy soil or clay soil, a ground screw is a good option in lieu of concrete to give you similar pull strengths. Compared to a concrete auger and pile, buying the ground screws or ground rods doesn't really save you much money. It really just saves you the lack of concrete. So you're paying more for these screws, and you're getting rid of the concrete truck. And for projects that getting a concrete truck out to site is difficult, these are good options. Otherwise, it's kind of a wash. residential ground mounts, I call them bleacher style or scaffold style, where you have two legs and then some framework in between. Um, depending on the post different distance, this can be complicated or simple. Tracking arrays don't have those two posts. Tracking arrays only have a single post. And utility scale ground mounts, similarly, even when they're fixed, they only have a single post, whereas residential systems have a double post. So why is that? I think a single post is much easier in terms of maintenance, because you can get a weed whacker or a lawnmower at least most of the way under there, whereas if you added additional posts along here, maybe with some cross bracing between, this section underneath can get kind of closed off. Well, keep in mind these single post systems are primarily pile driven, and so these posts, for every foot up they go a foot down. In general, rule of thumb. And so what that means is you're actually going, 6.5 feet to 7 feet deep with these posts to be within spec. And most rentable, Bobcat, use the Bobcat for material transport and for trenching and for augering and whatever. With the extension bits, only go down 6 feet. And so, the point is the pile driving, to get the depth that you need, you're using heavier equipment. Whereas if you go with the two bleacher, the two post system, the posts only need to be half as deep. So you're only going, 4.5 feet down. And that's something that a Bobcat is capable of doing. So it's just an easier, simpler install. And here's a picture of it being installed on a concrete form, or above the ground, or with ground screws. These are all just different strategies. The standard way is just to drill out, put the post down into it, pour some concrete in. But there's other options. In this picture, they're showing leveling on uneven terrain by basically using a band saw to cut off the tops of the posts. And then the caps that get put onto the tops of the posts have a little bit of play in them so that you can level right after that. I have found that when we used ground screws or ground helical piles and had a laser level on the Bobcat, and that worked just fine for leveling. But we were on a much more even terrain than this. You can find single post systems for residential, and while that is my personal preference, they're a little bit more difficult to find. When you go from a 60 cell module to a 72 cell module, sometimes the only things you need to upgrade are the mounting brackets for a slightly larger, taller array. And so, being able to fit 20% more cells onto the same racking for a small, 1 to 2% increase in project size, generally that'll mean 72 cell panels are best for ground mounts. And so here is a part where I'm saying, hey, tracking, it's so commonplace at the utility scale, but it's non-existent at the residential level. Don't get confused. That doesn't mean tracking is not cost effective. It's that no one's selling products in this area Let's see, we have a comment about that concrete ballasted system we saw. We've seen concrete ballasts being used as landfill caps that can't be penetrated. And yeah, that's kind of this kind of system is a concrete ballast system on a landfill cap. And what works on the landfill also works on a flat roof. So this is, I actually went and experimented building a horizontal axis tracker. I wouldn't do it again. I just go with a fixed in place ground mount. There's what we eventually turned the tracker into is simply just a manually adjustable ground mount that could be adjusted by seasons. And that's not so bad. You don't really see stuff like that at the residential professional market. You just see fixed in place systems. There is one company making dual axis tracking systems and selling them to the residential market. I have found them to be pricey. So I'm generally designing for like a mid-range market, aiming for, trying to get the projects to always be cost effective. And I see the non-tracking arrays outperforming, the added cost of double axis trackers. And even at the utility scale, single axis tracking at this time is more commonplace than double axis tracking. And they're actually looking at these bifacial modules as saying maybe this will be the difference because, on a double axis tracker, the modules are more up in the air. I don't like the aesthetics of a tracker, a big, giant solar plate that's in your face. I think it's kind of like the satellite dishes of old. But the users say they like them. I just don't think it'll age well. The areas where double axis tracking would make a lot of sense are in areas like construction zones. You're driving down the road and you're always seeing these solar panels on construction sites. There's not a lot of open space, real estate available on a construction site. And so having a panel be able to kind of fit anywhere and adjust would be a good use of that. Otherwise, I generally would start by trying to find an out-of-the-way piece of real estate. And then there's a question of, is tracking really useful on a residential site to begin with? What tracking will do is produce more energy in the morning and more energy in the evening, and then perhaps more energy in the wintertime as well. And the morning and evening energy, while, yes, you need to have enough energy to live off grid, the battery is there to store and make up for differences between, when you're generating the energy and when you're using the energy. So, instead of doing tracking, it might be more beneficial to spend the same money on, a larger battery, because inevitably in an off-grid system, you're going to have times when the solar array is producing way more power than you're consuming or even able to store, because you need the solar array to be reliable. So, the power grid operates in a similar manner where we produce more energy than we consume to have stable electricity. So, maybe you get there quicker with a tracking array, but, essentially it'll take a little bit of power off of the battery, but not, a substantial amount. And so maybe tracking in situations where you're actually selling every single kilowatt hour that comes out of the array, such as a grid connected utility scale array, is the best application for it. Um, Engineering documents can really help with remote site evaluations. I mean, things that are just not picked up in a satellite picture are like what's underneath the roof. You know, here's a drawing and it shows 29 gauged rib steel on purlins. When we get into our racking discussion, that 29 gauge is gonna be important. And I had never really, this I guess was earlier in my career. I had not seen a roof where the metal panels were just put directly on top of exposed purlins. And in fact, that's what the design said, and that's also what the site visit revealed. It's common in the attic to note the attachment between the rafter and the building wall. A common one is, are there hurricane clips or not? And yeah, it's a good idea to do that. You're putting more force on your roof now, so you want to you're lag screwing into the rafter, and then you want to reinforce the rafter onto the building wall. For designers or building developers who are queasy about putting a 1/4 inch lag screw into this 2x4, sistering or daughtering an additional 2x4 onto the rafter will give you more area to bite into. And it's actually not as hard as it sounds, because the installer should be able to figure out where their L feet are coming down into the rooftop. And so I don't know if the roof is looking particularly weak. You know, putting additional reinforcement inside the attic is possible. The racking design software will give you an insight to engineering data that you might want to look into. So here's a company that makes brackets for mounting to standing seam metal rooftops. And they say, okay, well, what is the what are you screwing into? Are you screwing into the decking? Are you screwing into the a metal purlin or a wood rafter or purlin? Is it 2 inches of wood? Is it 4 inches of wood? And then how many fasteners are you using? Based on that, it'll give you your pull strength. Generally, a safety factor of 3 is applied. And so, say, well, here are the allowable loads on our attachments to the roof. And so what I want you to look at right now is when you go into surface board, you're allowed 100, let's just say 180 pounds of pull strength. And when you go into rafters, you're allowed 630 pounds. So yes, going into the rafter is super strong, whereas going into the decking is not. And so this is for different orientations of the attachment. So we're going to come back to that. So one is 180 pounds and the other is, over 500 pounds. Just under 2, just over 5. So the railless companies say, because our solar array is really distributed, it's not on interconnected racking with interconnected clips. It's like we're installing 20 different solar modules on the roof rather than one interconnected rack. That's actually better for stress on the rooftop. I'm sure that's an advantage. I think there's other disadvantages. I think that interconnected rack that goes across the roof actually gives the roof some additional strength, so that if the building burns down, the roof stays together longer. So I think there's some elements that solar could actually add in terms of safety with fire prevention. I don't think it's all take. But they also say if you go into the roof on the surface of the roof, the surface board. If you don't need to go into the rafters, yes, going into the rafter is ideal, but if it's good enough to just go into the decking, then you don't have any misses. You don't have any pilot holes. And so, the fact is, we see that going into the rafter is the strongest way to do it. Going into the purlin is the strongest way to do it. So, on a metal roof, my preference is to screw into that purlin and then reinforce how the purlins are attached to the rafters. If they're just nailed in there, you might want to go and reinforce at least the purlin that the racking attachment is going on all across the roof, to make sure that you don't pull the purlins off of the rafter. As opposed to the clip where you're relying on how that metal panel is clipped to the rooftop, and the way around that again is to make sure you are as even in your load distribution as possible, which means you're clipping onto every seam as you're going across the rooftop. I look at this trapezoidal rooftop. So here's another product made by the same company to sit on top of a trapezoidal rooftop. And, I get wanting to say, okay, the water is down here, and so we want the penetration to be up here out of the water. The main problem I have with that is that this screw is just biting into the gauge of the metal, and that's it. Whereas here, it's backed up by the purlin underneath. And so, which is more watertight? A connection that has plenty of sealant around it, that is super, way over engineered, way too strong for what it needs to be, and the water just goes around it, versus something up further. But don't get me wrong, in the torrential rain, you can get water up in here, and then over the long term, this screw not being well seated into this metal kind of vibrates and expands and wiggles its way into a leak potential. And so out of all three systems, my personal favorite is in fact the one that pokes a hole in the roof right down in the channel where the water's going to be, but plans accordingly by making it an incredibly strong penetration. And so, when you're looking at the standing seam roofing panel spacing, if the panels themselves were spaced 4 feet apart, the allowable uplift would be 50 to 80 pounds before failure. And so, if you're going and spacing your attachments like you would on a shingle rooftop, if you're going with a 4 foot or 6 foot spacing on your standing seam metal rooftops, let's say you're putting a rail on top of the standing seam. And so you're like, I'm using rail because it makes a neater array, and my rail span only requires 6 foot on center attachments. And so you go and attach 6 foot on center to a standing seam metal rooftop. All of a sudden, this rooftop is only going to be, rated for, let's say it was on top of plywood, 25 pounds a square foot of uplift. Whereas if you stick to one panel per seam, you're going with over 100 to 200 pounds. And so the real question becomes, well, how do you know how much load is on these attachments? And for that, we have to go to the manufacturer website and do some sizing calculations. So we're on our way there. So we have some comments, roof penetrations added to an existing metal roof will likely void a roof warranty, something to check into before going that route. And, the metal roofing companies make products for gas vents and roof vents, but, that's the one thing to look at is, are there already penetrations coming out of that metal rooftop? Often there are, because solar's not the only thing that pokes a hole in the rooftop. But the roofing manufacturer may be making vent covers and hood covers to better assist you with that. One thing that I've done on standing seam metal rooftops to avoid the penetration issue is to penetrate through the roof cap. The purlin, that there's a little gap between the cap of the roof and the standing seam that comes with a little metal flashing, and that metal flashing is where I've knocked out for my internal cable runs for high-end standing seam metal roof systems, and that avoids poking a hole in the roof entirely. Speaking of poking a hole in the roof, the last place you would want to poke a hole in the roof is a flat roof. There's these little pads that go underneath the ballast that act as little rub layers. The last thing you would want to do is cut these pads with an X-Acto knife up on a roof and slash a hole through this roof surface. Flat rooftops, you can see it right here. There's some puddles of water on this rooftop. Flat rooftops, when they rain, they fill up with water. I've been on not this roof, but a different roof, where around the roof drains, there was actually a levee, a little elevated barrier that went around the roof drain, and the net result of that was every time it rained, the whole roof would fill up with an inch of water. On this design right here, the customer was pretty smart. He says, I know my flat roof. I know I get puddles of water on the flat roof, and the last thing I want to do is buy a ballasted system that sits, an inch up off of that roof surface, knowing that I get, a half inch or more of water on that rooftop every time it rains. I agree. There's really not much in electric code governing puddles of water underneath solar arrays. I think that's a area that needs a lot more insight put into. On this project, he said, I'm going to get a racking system that is elevated up off the rooftop. And we found a really good one that gave great clearance up off the rooftop. The manufacturer, Unirack, one of the top racking manufacturers in solar, they said, y'all are our last customer on this product line. We're discontinuing it because no one's buying it and they all want this stuff. So this is the common way, the standard way to do it. You have to be careful on your particular rooftop, taking the time to find a racking system that gives you some elevation off of the roof deck, I think is absolutely worthwhile. The problem that installers face is not wanting to poke a hole in a flat roof. They're terrified of the roof leak, and that drives maybe them not to consider some of these issues. If you elevate up off of the roof deck, you get more wind load, and that means there's more stress on the rooftop, and not all commercial rooftops can handle it. I mean, that's true. But the base case, the way that installers are anchoring solar arrays to commercial rooftops is to weight it down with concrete blocks. Concrete blocks are not supposed to be on a easy to damage, plastic roofing system. You have to be very careful to not stack too many up when you're staging the install. Walking around the concrete takes a lot of time. You don't want to drop them on the roof because then you'll gash a hole in the roof and then you'll need to patch it. And maybe the solar installer is not a roofer. So, what we found with this system is that we could eliminate the concrete entirely if we anchored the corners of the solar array down. This concrete is here pretty much to prevent the array from shifting laterally under high wind. These array sections get big enough and heavy enough, wind is not going to pick them up into the air. What's more likely is they'll find a poorly installed solar panel and rip that panel up off of the racking, but the whole thing, that's staying put. But in an earthquake or high winds, the concern is the lateral load, and so they're countering that lateral load by putting in tons of concrete. 5 pounds a square foot sometimes more. When you anchor through the roof, that same 5 to 8 pound a square foot commercial system becomes 3 pounds a square foot. It becomes substantially lighter. And some rooftops cannot take even that. Some rooftops can't take anything. Some rooftops were not designed for the load of the fire suppression system. And then when they added the fire suppression system to the truss, that overloads the building. And so not a single thing more can go on top of the building, and you just don't have a job site then. But if you do have a job site, consider cutting a hole in the roof with a U-bolt that goes around the building structural wall element to eliminate the amount of weight that's needed up on the rooftop. And so even these kinds of concrete ballast systems have options that throughout it there might be a opportune point to lay down a positive penetration, and that can eliminate the surrounding area's need for concrete ballast. And while it is a little more difficult to also have a roofing contractor out there making the penetrations and doing the seals, there are products for that specific purpose in the commercial roofing industry. This is a TPO membrane, and with a TPO membrane, you can actually melt the seal, onto it. I've seen PVC roofing systems. The PVC roofing system I installed on was not good enough for workers to simply be walking on, carrying the concrete. The best practice would be to put down a whole walkway for the workers to be walking up and down the roof on while toting all this heavy concrete up and down the rooftop, simply because the weight gets to be too much for the surface itself. So, there's a lot that can go wrong with concrete on the rooftop, even though that's the standard design practice. To the point where, I feel like installers need some education to say, look, a roofing contractor, whoever installed this roofing system can come out, cut a hole, and here they're tamping down the TPO membrane before they put the pipe boot on top of it, and the pipe boot comes with weldable material. And the end result is a very waterproof seal of that penetrating attachment point. This is something that I found that they do in Florida for just 150 mile an hour wind zones, where they're actually gluing the surface board and the truss together. The problem with that is it almost requires a complete rebuild when it comes time to finally take that surface board off the roof. But there are different fasteners you can get for improved roof strength. I actually hate that because when it comes time to prying up the shingle nails to get the flashing underneath the shingles, if the homeowner kind of upgraded to a stronger fastener for no good reason, it it really makes prying up the shingles more difficult and longer. When designing the racking system, and it basically you're taking your array layout and then just replicating it within the racking software. So here's our array layout, and it's a little hard to tell, but we've basically modeled it in the manufacturing sizing software and then kind of grayed out the areas where the solar panels aren't going to be. In this separate design manufacturer's design software, we are individually building each little section of the array within the design software. So we're either visually inputting the layout or we are manually entering the little sections of the array, like here's this would be one section. This would be another section, a little section of 4 modules, a little section of 4 modules, another section, another big section. All those little sections are entered into the sizing software, whether or not you're going in portrait or landscape. And then the sizing software says, okay, what's your regional 3-second wind gust speed? What's your snow load? And then what's the exposure category? Are there nearby objects to block wind, or are you relatively exposed? The more advanced racking manufacturers will actually ask you a little bit more information about the roof truss, the distances between rafters, the distances between purlins. This is the kind of stuff that a really good installer will be picking up and noting on a site evaluation, so that they can design the racking system with this information in mind. Like, if I already know the spacing between my rafters, I can design a system where the staggered attachment footings are have a tolerance built into them, so that regardless of where the first rafter actually ends up on the design, the staggered design will hold. If I don't know the rafter spacing, the installer is going to have to figure all that stuff out when they get to the job site, which they do, but especially for first time installs, that can lead to a lot of head scratching. And maybe it means you don't go with staggered L feet and go with something more simple. I'm just saying these are all design opportunities for someone who wants to start doing more solar design work and maybe enabling general roofers and general electricians to get into the marketplace. And so here they're talking about the different zones for wind speed. And at the end of the racking sizing software survey, it says, do you want the XR10, the XR100, or the XR1000? And based on the maximum spans between attachments and the maximum cantilever distance that the racking can overhang the last attachment point, we can tell that the XR1000 is a stronger, more robust system than the XR100, and likewise the XR10. And so the racking sales rep says, man, you're going to love our XR100. It's not industrial, but it's a lot stronger than the XR10. And so if you hated doing 4-foot on center attachment points, well, our XR100 can kick that all the way up to, over 6 feet on the interior of the roof. And even if you get to zone 3, which, zone 1 has a longer span than zone 3. Zone 3 is the corners of the roof. Zone 1 is the interior of the roof. And he says you're going to love the XR 100 because you have a lot of span in between your feet, so you don't need as many penetrations into the rooftop. This cantilever distance becomes important for aesthetics, so keep that in mind. A 1 to 2 foot overhang. Now, a solar panel's 3 feet, so if we actually use the XR1000, we could overhang the short end of an entire solar panel over the very last attachment point, but only if we used an XR1000 rail system. I did a site evaluation on a project that would be great on solar rescue, the imaginary television show where developers start installing solar arrays before they ever do the design work. And it was a pergola, and the solar panels are hanging off of the racking, and more than one panel is hanging off of the last attachment point. It's like, well, that either needs to change or we're not going to be involved on this project because that's going to bend and sag over time. And the racking spec sheets can tell you that. Then again, if you're going with, trying to hit every single rafter on the rooftop, particularly if you only have one row of solar modules going across the rooftop, you're only going with a 4 foot on center attachment point for one row of modules. The rafters are 2 feet apart. And so to hit every other rafter in a staggered configuration, you're only going with a 4 foot on center distance, sometimes less, sometimes, 16 inches times, 2, 32 inches. So, actually getting the cheaper rail system is often the best choice when your spans are going to be less than, 5 feet to begin with, because you're not spending so much money on the rail gauge. So this is the real data that you're looking for when you're using a racking sizing software. You've entered in the array layout, you've told it which rail you're using, you've told it how many spaces are in between your L feet, you've told it your wind zone, you've told it your exposure category, you've given it some roofing information, and at the end of it, it says, okay, if you're in zone 1, if you're inside the roof interior, you're going to have 170 pounds downforce on each attachment, 103 up with a lateral load as well. And what's interesting about this is as you get into the corners of the array, the downforce, the dead weight, the maximum snow load, that doesn't really change. The wind load is what increases, and that's an uplift force, not a downward force. The solar panel wants to get sucked up into the air, not pressed into the roof. And that uplift force becomes over 300 pounds at the corner of the roof, whereas in the interior of the roof, it's 100. So remember what we said about attaching to the roof deck versus the rafter. The rafter uplift strength, the rafter pull strength was over 500 pounds. It was like 638 or something like that. The decking was like, what was it? It was just under 120 pounds. It was like 173 or 178 pounds. And so the inside zone 1, the decking-based attachments are strong enough to stay attached to the decking by a safety factor of 3. Pretty good. Do decking-based racking systems that are attached directly to the surface board of a roof work? Yes, they do. Are there certain rooftops where the shingles are so bad that you just want to stay on top of them? Or the roof is a trailer and the attic is filled up with foam and you can't verify that you're hitting the rafters and you can't use a stud finder to determine it? And there is, by the way, a very expensive stud finder that can see rafters. Basically it's a concrete scanner and it costs $800, sometimes used, and it lets you see 4 or 5 inches into the space behind you. A regular $40 stud finder can only look at, a half an inch, but this is deep enough to get through the shingle and through the surface board and into the attic. High-end laser stud finder manufacturers make them for concrete scanning. They also work up on the rooftop. But if that roof is filled up with high density foam and you still might not be able to see the difference between the rafter and the foam. And so if you can't verify hitting the rafters, maybe designing it to be a surface mounted system is the best, even if you are in fact hitting the rafters. And this uplift force and downward and tangential forces comes from the racking specific data that they give you specifically for their racking system. And so here we see a distributed weight of under 3 pounds per square foot for a non-concrete ballasted or non-concrete system. Concrete adds to that. And so in this design software, they have it set up so that it's really easy when you're done with the process to get a line item list of material. And so once you have your array layout, you know what modules you're using, you know which inverters we're using, which we haven't covered yet, but we're getting to. And now you know every bit of racking you're using. There's not much more specialty material that can't be purchased on Amazon that you need. So at this point, you're pretty much assembled a bill of material that you can take to a solar distributor and competitively kind of bid out. We really need every minute of class that we can, so we are going to take our 15-minute break right at 12:30. But since we have a couple Central Time, but since we have a couple more minutes, let's keep going. Solar cells are wired into series called modules. Modules are wired into circuits called strings. We kind of looked at that yesterday. And so the entry level inverter is called a string inverter. And the problem with string inverters is when the grid shuts down, there are safety provisions built in so that the inverter does not backfeed the grid. And you can have a transfer switch and a battery and a partridge and a pear tree to, keep the home powered during that outage if you want to. All that adds cost. But if you're doing dumb solar, which is just solar panels and an inverter, when the grid goes down, you have to cut off the power, and that is built into the inverter itself. The problem is, even though the output of the inverter can be cut off, the input of the inverter remains active. And so if the power has been cut to the building because the building itself is on fire, then, electricity is killed to the building, but you still have live solar panels on the rooftop. And despite the lack of high voltage solar wiring deaths, there have been instances where the fire department has let the building burn down rather than fight the fire because of unknowns about solar safety on rooftops. And while these unknowns will probably continue on into the future, and there's still probably going to be firemen not going on rooftops with solar and letting the buildings burn down. National Electric Code has taken steps to reduce that from happening. You know, they've recognized it as a hazard and said, at least in the US, we're going to have higher safety provisions, and that's going to make solar more expensive, but it's also going to make solar more safe. And so the rule now is for rooftop arrays. It says, would the downward load not offset part of the uplift? Those loads in the past slide are your maximum loads. So when the wind is picking up the solar array, you're not going to have that dead load. That would be like when snow is sitting on top of the array. Anecdotally, so I guess this question was about structures. Anecdotally, I have seen a exposed picnic area awning where a tornado came through, and the half of the rooftop on this exposed metal standing seam roof that got ripped off was the half that did not have the solar array on it. So, you know, I do think there is an element of structural integrity that the solar array adds to the roof. And I'd say in that instance, the added weight from the array helped that side of the roof not get ripped off. I think there's some considerations on a standing seam rooftop. If you go with a rail system, the rail is going to go on top of the seam, and then the solar panel is going to go on top of the rail, and so you get a lot more air gap. You know, alternately, when you have a standing seam roof and you use a railless system, the solar panel itself is, you know, just slightly higher than the seam. And so you really don't have much airspace getting underneath the array, and you do have that added weight. So anecdotally, you know, putting solar on the rooftop, that dead load does seem to have a beneficial effect, but at the same time, the dead loads in that picture are not referring to the standard dead load, but rather the maximum dead load. Okay, so back to string inverters. Yeah, NFPA has code that says you have to put a little control box behind every panel on the rooftop, because when the building is in a shutdown mode by the utility, the voltage on this roof-mounted solar array has to drop below, it's like 90 volts or so. And normally this home run circuit is running at, you know, it's rated for 600 volts. It's normally running around 400 volts. And so the only way to limit the voltage of this conductor that is inside the array perimeter, you know, past versions of code have been a little bit less clear about what happens inside the array perimeter. But 2020 makes it abundantly clear that, you know, your conductors inside the array perimeter need to be de-energized down below 90 volts. And so that really mandates the use of these, what's called module level panel electronics on roof mounted systems. And so SolarEdge and Enphase have been doing just fine and tearing up the market share of roof mounted solar in the United States, because National Electric Code essentially mandates them. And so you have these little boxes that are behind every panel. So microinverters came to market first, and they do a full AC to DC to AC inversion up on the rooftop. I think microinverters are particularly great when you're only doing a really small solar array. You know, 4 kilowatts or less, microinverters are awesome for. For do-it-yourselfers, microinverters are also awesome because they're very easy to install. And for general electricians, you know, if you're trying to put a 4 kilowatt array on every single rooftop, Microinverters are a really good way, easy way to go. The problem with microinverters is that they're more expensive because you're buying an inverter for every single panel on the rooftop. And inverters are expensive, and they also fail. But these control boxes are mandated because of fire code. And so what SolarEdge has done is they don't do a DC to AC inversion on the roof. They do DC to DC. And so what they say is, look, this home run conductor is rated for 600 volts, but normally it's operating at below 400 volts and sometimes much less. And that's a function of module voltage. So in addition to controlling as a shutoff the module voltage behind every panel on the roof, we're also going to do voltage regulation. And so, one advantage of microinverters is it's all an independent system. And if one microinverter goes offline, the rest of the system remains functioning. So if one microinverter gets shaded, the rest of the system remains functioning. That's much harder to do with series wired products than it is with parallel wired products. And DC SolarEdge's system is wired in series. So what it does is it kind of communicates to each module what each module voltage is. And so it can actually take out the shaded modules in a similar fashion to microinverters. And so what that means is, these product classes, microinverters and DC optimizers, they were originally created for shade and partial shade conditions. If a shaded solar panel on a traditional solar circuit gets shaded, if the whole panel is shaded, it's going to block the circuit. Yes, there's these bypass diodes. If 1/3 of a solar panel is shaded, which is kind of ridiculous, it doesn't happen except for a few minutes a day, but whatever. If it enables the bypass diode and the bypass diode takes 2/3 of the panel out of the circuit, it'll take 2/3 of that circuit out. If a panel is completely shaded, it'll take the whole circuit out. And so it used to be back in the day, you had to avoid shade like it was the Black Death. And you stay away from it. Don't go anywhere near it. Well, with microinverters and DC optimizers now, you don't have to worry about shade because there are spaces on the rooftop that if it got shaded until 9 or 10 o'clock, if it's just that one solar panel, you would still want the solar panel there to begin with. And even if that particular solar panel is shaded for half the day, the aesthetics might say 1 or 2 panels that catch a lot more shade than the others is acceptable as long as it's not a lot of them. And so these products were developed for shade mitigation, but they also just happen to play in well with the latest and greatest changes to electric code, which mandate that on top of rooftops, you have to have module level shutdown now. So you still have string inverters going on by themselves on top of rooftops, but that's generally in areas that are still not really enforcing NEC 2014. Now, I think NEC 2017 was also vaguely worded to say that we're not yet regulating what goes on inside the array perimeter. It used to be in past iterations of code, they were more focused on outside the array perimeter, but now they are regulating inside the array perimeter as well. And so what we can see is Enphase in yellow and SolarEdge in green. Enphase came to market first in 2010. At the time, SMA really was the king of the mountain. Enphase immediately started taking up tons of market share, and then SolarEdge came to the market with a slightly different platform. And SolarEdge's slightly different platform gives it a slight cost advantage for very similar advantages as Enphase. And so what we've seen is SolarEdge, despite being later to market, has grown larger at this point in time than Enphase. And so the advantages of microinverters and DC optimizers is that during a power outage, they will confine the voltage to module level voltage, which is only about 40 to 50 volts. And without that box regulating that voltage would be adding up to be high voltage, and the firemen don't want that when the building's supposed to be dead. The cost advantage of the SolarEdge system over the microinverter system is buying a whole bunch of inverters instead of one string inverter is expensive. Buying 30 smaller things instead of one bigger thing, the 30 smaller things are more expensive. And so what SolarEdge has done is they've taken half of the microinverter, just the DC side regulation, and put it on the roof. And the rest of it they've kept inside a string inverter. And so the string inverter now gets constant voltage rather than variable voltage. And that means with SolarEdge, you're buying a string inverter and these module level boxes, but the total system is slightly less money than the microinverters, to the point where most solar installers prefer the SolarEdge platform over the microinverter system. But do-it-yourselfers, the microinverter system is very easy. So with Halfmoon's array, we went with microinverters because we didn't want to involve a solar contractor. We just wanted to use the regular electrician who was willing to get up on the roof to do the install. And certainly if you're just working with an electrical contractor and a roofing contractor on your project, and the project is relatively small, microinverters are a good choice. And they make kind of similar microinverters to go up on commercial rooftops too. This one was really focused on string level, which the National Electric Code now does. I think National Electric Code should allow string level to count, but they don't. SolarEdge makes a system where you put 2 panels on every one controller, which is a little bit more cost effective than a 1-to-1, although more difficult to wire. But here we have a picture of the microinverters up on the rooftop, ready to be installed. The panels go on top of them. The panels plug into them. I forgot about our break, so we're going to break in 2 minutes, and then we'll start back up at the top of the hour. Sorry about that. And so again, this is all about rapid shutdown. And in the past, the rapid shutdown boundary has been like 10 feet. So all conductors outside of 10 feet need to be de-energized. And that was like NEC 2011. And then NEC 2014 came around and said, actually, we're going to make it 1 foot. And so all conductors outside the array perimeter by 1 foot, including subarray sections, so the jumper cables between subarrays now need to be de-energized. And then NEC 2017 came around and said, it's a 1 foot, and we also want you to start shutting down inside the array perimeter, but they made it kind of ambiguously worded. And now in 2020, it's, you have to, all the conductors inside the array perimeter need to be down to below 90 volts during a de-energization mode. which is really too bad. You know, the junction boxes were beginning to incorporate electronically controlled circuit disconnects, so that it's really easy now to just use the cheaper string inverters and disconnect the power outside the array perimeter. But code has gone into the array perimeter itself, and so just string level controls don't meet the strictest interpretations of NEC 2020 when on top of buildings. And so in terms of cost, just getting the string inverter by itself is the cheapest route. You wouldn't really worry about smart combiners anymore with the latest and greatest code updates. So where you would do a string inverter is on a ground mount array, you know, where you don't have the rapid shutdown requirements. The string inverters are great for ground mounts. They're a little bit cheaper. Solar installers go with DC optimizer systems, which are cheaper than microinverter systems. I'd actually say this is maybe a commercial pricing. You know, when you get to residential, it's closer to 26 cents per watt. And then if you do the residential option with the battery capable inverter, it's even more expensive. It's about 33 cents per watt. Whereas microinverters, you know, around 39 cents a watt, sometimes a little less. But they're more expensive than their DC optimizer cousins all in. And so generally from moving from microinverters to DC optimizers, you can shave a year off of your payback in the low cost area part of the country. In high cost areas, the cost difference between DC optimizers and AC microinverters are closer together. So, you know, you get a better, you get a quick payback either way. And so sometimes the upgraded part in a high cost area is worth going for. Yeah, so now we're going to take our break. Sorry for going over. It's about 13 till or so. We're going to pick back up at the top of the hour. So let's take about a 10 to 15 minute break, guys. That's what we'll take, and we'll be back at 1 p.m. Central Time, 2 p.m. Eastern. So we're going to pick back up in about a minute. Okay. Come back to this later. I don't know. Let me get back to the program. All right. Come on. Okay, welcome back. We're going to talk about some battery components for a minute. So where the kind of optimal solar platform is coming out is, okay, we need these little module level boxes behind every panel on the roof. And what that's also going to give us, because we might as well have these boxes do some voltage regulation, do something useful. And so they're regulating the voltage and keeping this DC home run voltage nice and stable. And there's some cost savings benefits to that, because now the inverter can be cheaper because you've taken some of the parts out of it and put them up on the roof, but not all of them. So SolarEdge is starting to get a couple of kind of copycats. Batteries, too, benefit from a high DC voltage run. We're used to thinking in the off-grid battery sector as a high voltage battery being 48 volts, but the problem with that is the grid is at, we have these 120 volt devices, sometimes 240 volt, but each leg's 120. We have a 240 volt electric service that's rated for 200 amps per leg. Volt times an amp is a watt. And so if you decrease the voltage from 240 volts to 48 volts, then you're increasing the amperage. And if we're starting at 200 amps, to pull a full, 200 amps worth of AC electric service out of a 48 volt battery bank, you're cutting the voltage down by 80%. And so, now you're looking at, a 1,000 amp system on the DC side of things. And that's way big. That's not even one big thick battery cable. That's multiple big thick battery cables. I mean, it's really untenable. And I'm starting to see some errors in design where the battery is too small for the inverter, because they want an inverter that's large enough to back up the entire house, but batteries are expensive, and so they just go and find a 48 volt battery and connect it to the 48 volt battery inverter, and they don't stop to think that, at full rated power, that thing would be pulling 1,000 amps out of it. And in reality, these whole house solar backup inverters are not 50 kilowatts, which is what your service panel can pull. But, the largest one that I see is for residential is around 12 kilowatts. But even so, at 12 kilowatts, you're still pulling 250 amps out of your 48-volt battery bank. And some, most, even the best 48-volt top shelf ultra expensive batteries are really only rated for, the top one that I know of is 150 amps out of it. And so you would at minimum need two of these things in order to make the rating of 250 amps. And really what I'm trying to say here is uh, batteries benefit from higher voltage, because the higher in voltage they go, the lower in amperage the output's needed to power the home. And the only way you get to a whole house backup battery is either to have a giant flooded lead acid battery at very thick high amperage. Like if you have a 48-volt battery, even if it's lithium ion, you're going to be at this giant amperage amount that requires you're spending all your money on your cable and not on anything else. And so where optimal solar design is going is saying, hey, we're going to have some high voltage solar on site. It also benefits us to have a high voltage battery. And the question is, are you gonna put it into the solar and the battery share the same inverter or not? And the optimal configuration is to do something like this, except there's not a lot of products on the market that are kind of servicing the optimal configuration. Instead, it's more like, we already have on-site solar, and how do we add a battery to that? And so should the solar array and the battery be kind of separated and on their own equipment? And there's a lot of nuance between what size battery inverter and what size solar inverter, and should they be combined or separated? And if they're combined, what does that mean in terms of switchgear and infrastructure versus separated? There's a lot of technical expertise that you need to know that you're not going to get out of a standard solar installer who doesn't have any battery experience. These systems can get very complicated, and there's there's a design technique for taking a camp that's only powered by diesel and attaching a small solar array to it, and that's very different than the same camp where if you wanted to offset and do a really large solar array, then you have to have batteries, controllers, switch gears. So batteries do complicate things, and that's why most grid-tied batteries, they kind of cheat, and they say, we're gonna work with your solar array to optimize your electric bill, but really they're only powering a critical load panel. And for many of them, any kind of intelligence that they're advertising is only going to be applied to that critical load panel and not the rest of the house. We're going to come back to some battery discussion in a little bit. I'm going to put the cart ahead of the horse here. I guess what I was trying to say is there's some more complicated things when it gets into battery design, but the optimal design is looking at DC optimization on the roof and a shared DC bus for high voltage batteries and high voltage solar and high voltage electric vehicles. But we're far from like there being a consensus on that. How do you design something more simple? How do you pick out how many solar panels are being wired up to the inverter and what kind of configuration? Well, there's a sizing software out there. It's called string sizing. And it's gotten a little bit more complicated because string inverters have gotten a little bit more functional. It used to be that shading one solar panel on the roof would ruin the rest of the system. Just any amount of shade was horrible. And that led to the rise of microinverters and DC optimizers. Well, now string inverters will often have multiple controllers, multiple, they call them power point trackers. What is the maximum power point tracking to make the system operate at the best voltage and the best amperage? And the shaded solar panels interferes with that power point tracking, and so now they have like multiple core processing to have one section of the array track differently than the other. So modern string inverters are more shade tolerant than they used to be, and they can handle modules facing different directions, whereas in the past that wasn't the case. But they still don't do the rapid shutdown functionality, and so you really can't just have a string inverter on a rooftop anymore in the United States. So this is SolarEdge's system. They are a DC optimizer company, and basically what we're doing here is putting in how many solar panels fit on the rooftop. And since each individual panel is being optimized, the tilt and orientation of the array really doesn't matter anymore. All it's doing is looking at the solar panel that we're using, the spec sheet, and looking at its volts and amps and watts, and determining whether or not it's compatible. You know, this is a thin film solar panel, so it's really weird in that it has an extremely high voltage. So it needs a special voltage regulator or DC optimizer. 72 cell modules need different optimizers than 60 cells. You know, this sizing software tells us what is compatible. And so, you know, our solar array is 40 kilowatts. And so, you know, SolarEdge is telling us we need a 10 kilowatt inverter, 2 of those inverters, 3 circuits each. And there's going to be, you know, 11 optimizers per circuit. And we need this P405, and there'll be 2 solar panels for every optimizer. So it's kind of designing our electrical layout for us. You know, in this platform, this is just a regular string inverter, and it's saying, okay, on one PowerPoint tracker, you could have 1 circuit of 9 modules, and you could have 2 circuits. You could have 2 circuits of 9 modules. You could have 2 circuits of 10 modules, and on the other one, you could have like another independent circuit. Might as well just jump online and do an example. You know, so this is a string inverter company, Fronius. I think a budget but quality. You know, I'd say they're a mid-range inverter company. Going into their string sizing tool. I don't want to do a download. There we go. And so what we're putting in is, you know, our electric code, and it's probably going to say, oh, you need optimizers. So let's you know, just do this for a ground mount string inverter. The temperature range. So at cold temperatures, voltage is going to go up. And so this is constraining us to make sure that our circuit does not exceed the operating window of the inverter. So, you know, right now we're designing our system to go down to 16 degrees Fahrenheit, you know, and that's based off your local area. In other areas, it can easily go into the negatives. And then there's a little bit of flexibility here too, because often the coldest temperature, design temperature, is at night, and you know, the panels might be a little bit warmer in the day. But it's, you know, how much of that risk do you really want to take on? I mean, there's charge controllers out there for extreme environments that will intentionally delay the startup time of the system to allow the panels to warm up so that the voltage drops a little bit and stays within the parameters of the system. But most inspectors are going to want you to see these temperatures on the cold end to be the record low in your area. On the hot end, it's not really a voltage or safety issue. It's more a performance issue. You just want to say, okay, in the summertime, if it gets up to 115 on a regular basis, that's what you want to design it around. So the voltage is going to determine how many modules can fit on a circuit, because that'll determine the maximum voltage, and you have this upper design constraint of 600 volts. The amperage part is more like heat drags down performance. And so you don't want to make the system so small that it doesn't turn on in the morning on a hot morning. So, the record cold is what's generally used, whereas you don't need to use the record high. You can just keep it as is. And so it's asking us, 600 volt system, 1000 volt system. You could do 1000 volts on commercial. It's more cost effective to do so because you have longer circuits. You can select which inverter you want to use. In our case, we're going to use a 7 points. Really what I would say is I look at my inverter sizes and I say, okay, maybe a 6 kilowatt inverter is fine if I have 7 kilowatts of panels. Undersize the inverter a little bit. You can go to PV watts and generally see that most systems are, can tolerate a 15% undersize on the inverter level. Anything more than that, you start cutting it close. We have to pick out our solar panel, and now we get down to our configuration. So if I look at my array layout, I'm like, okay, on this side of the roof, it's real easy to do 18 panels. So I'm going to do 2 strings of 18. For the last remaining circuit, it's telling me, the largest I could do is 1 circuit of 10. And so if I bought 25 solar panels in a typical pallet, it does vary. You have to get that on the spec sheet. If I have 25 solar panels, I could do, 2 circuits of 8 panels, that's 16, and then 1 circuit of 9, and fit that on a string inverter. And the parameters adjust based on telling me what is acceptable. So this is the Fronius string sizing software, and it only it's every single inverter company out there has string sizing software available on their website to download, and then commercial software incorporates this just directly within the commercial interface. So the string sizing software will tell us how many modules will go on how many circuits. But the solar designer has to determine where those circuits lay out and how on a rooftop. And there's a little bit of an art to simplifying the install. What a really good design, a really happy solar design, it would start the circuit at the end of the row and then just run the circuit all the way across and then end it there. So that a solar installer who has no clue about the actual design of the system down the road can go and do some maintenance work. What's common is the installer to design with the fewest circuits possible. And so when you're going with the fewest circuits possible, you get this kind of snakes in a basket approach where there's the start of our first circuit. Here's our second circuit. I'm using different colors and being fancy, but here's the third circuit. Maybe like so. And all of a sudden, where the circuits, start and where the circuits stop becomes pretty jumbled. And so if you don't have a circuit diagram layout from the original installer, if there's something that goes wrong on this array and you have to get up there and start troubleshooting the hard way, with a voltmeter and visual inspection, you're flying blind without knowing where these circuits start and stop if you try and design with the fewest circuits possible. And so if your inverter system has the ability for one or two more circuit terminals that you're not using, whether the circuits are running across the roof, which is generally how it's installed, and so that's easy to wire, or whether the circuits are running up the rooftop, or if it's a weird design and there's not a good one, making the circuit layout as regular as you can, and then just leaving another accessible endpoint to be funky, is going with more simplified circuit layouts is important down the road, when project documentation is not readily available for an untrained expert to be able to figure out what's going on in terms of maintenance. Here's SMA's string sizing software. Again, you're putting in which module you're using, you're putting in which inverter you're using, and it's just going to tell you how many modules go on how many circuits and what's acceptable and what's not. This document is made by commercial solar design software. This solar design software, if you research the most popular solar design softwares, would probably not even show up on the top 10 list because they, don't have as much money and do a much more limited scope than others. It's called Solar Design Tool, and they really only focus on small to medium batteryless residential arrays. But it's incredible what they've put together, because this is a CAD file that is pretty much ready for project permitting. And it's 100% computer generated. Nothing about this is hand drawn within CAD. So you go through a survey where you pick out the components and you tell it what it is. But National Electric Code is a rule-based design system, and so those rules can be programmed. And so computer-assisted design for code compliant systems really is the way to go. Not leaving the design decisions completely to human control, but having a tool to help you design with the bare minimums. Just know that there is computer-assisted design software out there that is all programmed for you. Now, most of the software out there, Solar Design Tools being a little ballsy because it's trying to provide you with a complete permit package. And a lot of the more professional commercial software, they want the designer to be responsible for that. And so they'll give you the one-line diagram, but you have to export it to CAD to finish out. Solar Design Tool, for its scope, is very complete, and I'll often use it to start a project and then export to CAD to finish it up, in terms of creating documents for building permits. So here's some examples of other capabilities of computer-assisted solar design. Conduit fill calculations, voltage drop calculations, ampacity calculations, sizing up the smallest grounding conductors. And I might look at some of this and say, okay, well, the design tool has told me that, I can have some number 10, some number 4, some number 2, and some 2-watt. That's pretty purpose driven, so I would go with that. I might look at my PVC conduit and say, okay, well, this number 2 run is going to require me to be 1.5 inch diameter, and the other runs require me to be 1.25 inches. So I'm going to stick with, 1.5 inch conduit for that. You can do some, simpler, material SKU optimization. So a few of the commercial solar design softwares will count the equipment used in your balance of system design to generate a material list. You have to provide pretty complete project information for this stuff to work. That's kind of the biggest challenge I have is, while I can create very rapid one-line diagrams, there's a survey process involved. So if you don't have the information for the survey, then you don't get a good one-line diagram. And so that's it guides my own site evaluation process. I think a great way to get into the industry is to sign up for any commercial solar design software trial and then try and get through the design process. But that's really other trainings for other days. Let's talk about interconnection. Where do you connect the solar array to the electric service panel? We got two options. The first option is a supply side connection. The other option is the load side connection. So the supply side is between the meter and the breaker. So you still get credit for this as on-site energy. It's on your side of the meter. But generally, the utility considers this to be their side of the service, whereas the load side is what you connect all your electrical loads up to. Now, there are very specific allowances on when you can connect something to these utility feeders, and it all has to do with on-site power generation and management. So solar, batteries, emergency systems, generators, all of these things can be supply-side connections. What is really more special is the ability to do a load-side connection, to be able to connect a solar array to where there's loads rather than it be a dedicated supply. And it's allowable. So, do I have a slide on this? Maybe not. We'll just do it live. What you need to know is that a supply side connection, it's like 100%. If this is a 200 amp electric service, it doesn't matter if the power comes in from the utility or through on-site solar or batteries. Whatever is feeding into this can feed up to 200 amps because the conductors are sized for it, because we have a 200 amp electric service. And so whether or not all of the solar array goes into the home at 200 amps or less, or whether that 200 amps goes and flows out the meter, or a combination thereof, this service is rated for 200 amps. It can take 200 amps. 200 amps times 240 volts is, almost a volt times an amp is a watt. 200 times 240, it's almost 50 kilowatts. So you can put almost a 50 kilowatt solar battery generator energy system as a supply side connection, as well as controllers to manage them. So you could really do 50 kilowatts of generator, 50 kilowatts of solar battery. You can do a lot with the supply side. But to work on the supply side, you got to call the power company and yank the meter to de-energize these lines. If you don't call the power company, you can de-energize the main breaker and de-energize the top of the service panel, but still it can really freak out non-electricians who are working behind a service panel that's actually live. And really, non-electricians should not be working a live service panel. It is super easy to call up the power company and get them to come out sometimes the same day to pull a meter for service work. It's more complicated to schedule inspections and stuff like that, but simple meter pulling, they generally will work with you. But but while it's impossible to do a supply side connection without the utility coming out and pulling the meter, I suppose nothing's impossible, but you shouldn't do it regardless. For this kind of work, deep sea underwater welding, sometimes hot connections need to be made. Solar, residential solar, call the power company. But on a load side connection, many installers say, nah, we're going to do a load side connection. We're comfortable working behind the main breaker being tripped, and we can wire up to here. And so it becomes, what is the size of the solar array that can be connected to the electric service panel? And the answer is 20%. So you take 20% of that main breaker rating. If it's a 200 amp panel, that means to the same service panel, you can connect 40 amps of solar as a load side connection. And why is that? The concern is that all of these breakers, if you count them up, they're going to be greater than 200 amps. There's assumptions being made that not all of these loads are at the same time, are on at the same time. But what would happen if you drew more than 200 amps through that service panel? Well, the main breaker would trip. So if you pull 200 amps of load through a service panel, there's 300 amps of breakers on it. So you pull 300 amps through a 200 amp panel, the main breaker trips, and you don't burn up your conductors. Well, if you have solar feeding the other side, you could pull 300 amps of power through a 200 amp service panel and set things on fire that way, because amperage heats things up and burns things down. Voltage, more explosive. So it's really not the amperage rating of the main breaker. It's really the amperage rating of the box and the bus bar itself. And so if you have a 200 amp rated box, you can put 40 amps of solar on it and 200 amps main breaker. If you're really up against the wall, you could downsize the main breaker and put a larger solar array and solar battery on it. So like you could do 125 amp utility service and still have a 200 amp panel and 200 amp service from the mindset of the customer if the solar side was large enough. The key to get that extra 20% allowance to be able to feed a service panel with more power than it's rated for, to be able to put 200 amps of utility line plus 40 amps of solar for a total of 240 amps, you're allowed to connect that to a 200 amp box if and only if the feeds are connected at the opposite ends of the bus bar so that they can best evenly distribute that power to the loads themselves without, stacking up their combined energies to exceed the rating of the actual bus bar. The bus bar is the literal metal that the electricity flows through behind this main breaker. So as long as that literal metal is not overloaded, it's not going to heat up and catch fire. So this is a rare example of where electric code is being flexible. Saying, you know what, that bus bar is rated for 200 amps. we're going to let you put 240 amps on it as long as you're at opposite ends of the bus bar. If you plug the solar array anywhere else, then the total breakers cannot exceed the main breaker rating. And so this is where I'm just a fan of supply side. Load side is cheaper, load side is simpler, and sometimes cheap and simple is the best starting point. But to me, what you really need as far as long-term planning goes is if this is a 200 amp electric service, what you really need is a 200 amp automatic transfer switch and a solar array and a battery bank. And the only way you're going to get to that point, eventually this 20% margin is just going to be too small. So eventually the house with a solar array on it will also need a battery. Eventually you're going to run out of amperage. Eventually you're going to need to do a supply side connection. So whether or not you start out with a supply side connection or get there as part of an expansion project down the road, that might be a matter of budget. But if you have the budget currently to spend, thinking about the supply side connection at the residential level is not a bad idea. Yeah, so the code for the 20% rule is like in section 705, which is interconnected power generation systems. I think it's 705.12D4. I'll send that in a text message to you. So it's a common rule. It's the solar industry refers to it as the 120% rule. Okay, so here we are on the back of the building, and we want to discuss our interconnection strategy. A Halfmoon's electric room, a little crowded and messy. Surprisingly, this is code compliant, except for the storage stuff occurring in front of the service panel. But the HVAC is 6.5 feet up. The gas and water lines are isolated from the electrical workspace. Everything else here is low voltage stuff. So, but even so, I'm not too keen on bringing the electrical inspector in here if I can keep him outside the building during inspection. So supply side connections often occur outside the building. So if you have particularly bad service panels, if they're not so bad that they're hazards, but you don't want to have to redo the whole electrical room because of appearance, you can keep the inspector outside by going in outside the building. So here we have our 400 amp electric service. And the service is coming into this 400 amp box, and then we have two 200 amp feeders going into the back of the building, and that's where the two 200 amp panels are, here and here. And what we were able to do is get the installer out, the building electrician out ahead of the project even. Utility pulls the meter. We take the conductors out of the LB from the service panel, and then out of, pulling them out of this LB so that this box is completely empty. And then we swap out this LB with a junction box and put the conductors back into the service panel. So all in all, that is under 2 hours of work. In fact, in opportune cases like this, it can be, less than 30 minutes of work. And from that point, we had our disconnect switch and a service panel. We went with microinverters, so this was just the AC service panel, and then stubbed up to the roof. So we went with a supply side connection on these feeder conductors, and that means we could put on these 200 amps worth of conductors up to a 50 kilowatt system. We only went with like a 20 kilowatt system. The inverter connection needs to have overcurrent protection. So that could be breakers on a service panel. With microinverters, breakers make sense because you're having multiple branch circuits of microinverters. But if you only have one big string inverter for the entire system, you could do a fused disconnect switch instead of a service panel. And generally, that's the cheaper way to go. Not necessarily the best way to go. Sometimes having some power circuits for energy monitoring or whatever is useful. As far as the actual connection, how do you intercept those utility feeder conductors? Well, there's taps where the utility feeder can come in and the line to the feed goes out, and the solar array comes in as well. And the trick with these taps is you still have to have your overcurrent protection on your main breaker and your overcurrent protection on your solar array so that you don't kind of have two of these taps backfeeding one during a fault situation. These are pierced insulating connectors. Sometimes the tap work is very difficult. Now, this is big, thick cable. It has to be well terminated, and it takes, some really strong hands. And, this stuff really, this is only master electrician work, or very experienced journeymen to get these things right. The piercing insulated connectors are very easy. They just clamp and bite into the cable. So they're a little more expensive. They go a lot faster. Talking with real master electricians, not mechanical engineers who've passed the master electrician exam, but the guys out in the field who are working on electrical services every day, they tend to prefer the regular tap connectors. They don't really trust the piercings to integrate with the insulation well, although these are UL listed products. They're also made for hot connections. It's a little too fancy for me. And so it's possible to just have the string inverter and the disconnect and all this stuff on your wall, or with a microinverter system, you can get an all-in-one combo box and almost have nothing on the wall. Both are code compliant in most jurisdictions, although I haven't confirmed this, but I believe NEC 2020 is actually mandating a knife switch disconnect on the side of the building, which looked like it was going away as a requirement, but now seems to be coming back. So some jurisdictions do not require the knife switch. They, I think, rightfully view this knife switch as a hazard. Someone can get into the knife switch, stick their hands into it, and not realize that when your knife switches are, disconnected, they're still hot from one side. So this is, now that we're on this topic, I should share it. The hot side of a disconnect switch, which is the grid side, because the solar array turns off when it's de-energized. So you could think, is my solar array a line or a load? Since you have the supply on this side and also supply on this side, the utility side should always go to the top of the switch. That can get very confusing if you have underground utilities and solar coming in from the rooftop. You might think, oh, it's just going to be easy for solar to land on the top of the switch, utilities at the bottom. The answer is no, because when you open these things up, the bottom side of the switch is more accessible than the top side. And so the top side, the least accessible side, should be the side that's always energized, with the bottom being the one that's de-energized during the disconnect. It's just safer that way. So we talked about the one-line diagram, and keep moving in the interest of time, but again, all this is computer generated. We've talked about balance of system clips and string optimizers. They do make string optimizers for commercial projects. That can be 1,000-volt optimizers or even higher than that. I think these are great. I think they are worthwhile even on a utility scale project. Oddly, though, I just don't see a lot of them. So I think string optimizers. What's neat about string optimizers is just like the Solar Edge module level panel electronics, it'll step up the voltage of the home run circuit. So particularly on long distance ground mounts, string level optimization where you can step up that voltage before transmitting the power down the line can actually save you a lot of money in cable fees, cable costs. What's really holding back the amped optimizer is there's not too many 1,000-volt inverters out there, 1,000-volt battery inverters. If there were, they'd be a great product. So here's some balance of system. Here's a plumbing vent product that if the plumbing vent is coming up inside the array, it can be plumbed under and out the vent. When you are replumbing vents, this is actually pretty interesting. Solar installers look at these vent stacks. They say, well, why are vent stacks the height that they are? Because if I could just cut the top of a vent stack off, it would fit underneath the solar array. And if the vent stack is that tall for snow, then the solar panel's protecting it from snow. So I'm going to cut the top of the vent stack off and cover it up. Well, the reason why the vent stacks are tall does not have to do with snow. They're tall so that the gas will dissipate into the air instead of kind of collect and pool on the roof and get heavier and go back down into a window. And so by putting the vent directly underneath the panel, if it's a gas vent, you're going to accomplish, exactly that. You're going to violate building code by cutting the top off and putting it over because you're causing the gas to collect, which is why the vent stack's so tall to begin with. So the best thing to do is just replumb the vent stack on the rooftop up and under the solar array. Which would have made this array we saw from yesterday look so much better. So digital controls is something that is kind of near and dear to my career interest at this point. Certain things in our home can help us not need so many batteries. Having an extra refrigerator or freezer could be viewed as a luxury in the past. But if I had a refrigerator full of soda, or even not have it be a dedicated fridge, but if I just normally used one refrigerator, but I could fill it halfway up with thermal mass and then have two refrigerators refrigerating the same amount of stuff as one, except they have thermal mass inside. You know, if I have one deep freeze, instead I have two deep freezes, but I just fill the bottom up with half-gallon jugs of water. You know, what does that allow me to do? Well, that gives me some thermal storage capacity. Your hot water tank, has thermal storage capacity. Now, I love hot water tanks because what a hot water tank is a really high load that does not always need to be on. And so if you could take that hot water tank and turn it on and turn it off as a function of your load, then you could take the tank off during peak times and reconnect it during off-peak times. If you could have your solar hot water tank work harder during the day and easier at night, you could sync up your building energy with its on-site solar array, or even better, optimize it for batteries or time of day rate structures or variable rate structures. And the same thing can be done, albeit a little more daringly, with refrigerators and freezers, thermostat controls as well, even smart wall plugs. So all of your heavy load appliances that are electrical could be fine-tuned to better synchronize with on-site solar, batteries, or neither, just to game an electric rate structure. And so I'm doing that exact thing on my house. I have smart outlets, a smart thermostat, and then the trick is I add an energy monitor that monitors my real-time energy use. And Halfmoon, we're actually going to do a 2-hour class on this, but I have a peak rate time between 6 and 8, where my electricity costs 36 cents a kilowatt hour. And then on all other times during the winter season, my electric rate is 4.5 cents. And so I'm taking my electric tank hot water heater and my air conditioner and my otherwise always on dehumidifier, and I'm turning them off during peak times and turning them back on again right when peak times are over. But in a different mode of operation, I could also take the tank hot water heater and make sure it runs whenever the air conditioner is not running, so that instead of using 8 kilowatts of load, I can get my home load to be below 4 kilowatts. And I'm doing this professionally, so I'm just going to show you kind of inside kind of data that I'm collecting. The house voltage is nice, thermostat controls, energy meters, and what I really like are the automations, where I have, right now I'm running an automation for time of use metering, but then there's also demand management automations that are very, very basic and surprisingly easy to program. So here I have in my smart platform, I have an energy meter, and whenever it reads below 1,000 watts for 15 seconds, it turns my dehumidifier back on. And so this is my automation to turn my dehumidifier on when my building load is low. And then I have another one to turn it off when the building demand is high. I have a customer living off grid using this system to get more out of their battery inverter and to live within their output capacity. At the same time, there's markets like Arizona that have residential demand rate structures where that's easy for demand rate charges. And in fact, it's kind of, this smart appliance stuff is kind of making me have a little bit of an existential crisis as a solar installer, because in many cases, load control can't do your entire electric bill like a solar array can. So there is value in power generation, but many times this digital control stuff can be way more cost effective in terms of payback than solar or batteries. But I view it as kind of a missing piece of the puzzle. Net metering, where you're selling back every kilowatt hour of electricity for near retail value, kind of eliminates the need for smart load control. But there's a lot of markets out there where the solar buyback rates and policies are getting worse, at which point energy monitoring and load control becomes much more important. So here's some pictures of cable trays for bringing cable back along the rooftop. What you can see in this picture is conduit coming out of the array, and then it transitions into cable tray. Cable tray is way more expensive than using just regular conduit, but it is the professional way to go about it. So I like buying my solar racking with cable management pathways built into it to kind of eliminate the need for buying cable tray within the racking system. But particularly for commercial rooftop arrays, when you get outside the array perimeter, that's the time to transition into raceways and cable tray for your home run. In fact, the fire hazards from the big commercial solar fires have all been from conduit pulling apart. It could be professionally, well made up conduit, but if this conduit support is like anchored in place, that alone can cause the conduit to pull out of a fitting. So if it's if you size your clamp to be the size of the conduit and not one size up, you're securing the conduit permanently to a fixed in place position, and thermal expansion can pull it apart, and then the rough edges that are exposed can eat into the conductors, and the conductors can cause a ground fault. So I think that you will want to use on commercial projects cable trays in lieu of EMT runs that are paralleled together. We talked about snow guards and rodent skirts, so let's get into a solar economics discussion. Here's a sheet that's just some example of common items that we've talked about in class. So if you want to know what, solid bare grounding wire or number 10 PV wire or Mc4 connectors, lightning arresters, it's sometimes useful to know what these prices are. But the takeaway is even a few years ago, solar could be a do-it-yourself project. The definition of do-it-yourself still reserving some money for some qualified labor to help you with the task, as well as proper tools and equipment. But even back in the day, it was possible to do solar below what the national average pricing is today. And so really back in the day when you had big upfront grant opportunities, there were some opportunities to, do your own large commercial solar projects and really walk away with a tremendously subsidized, therefore profitable to the developer project. So like back in 2016, we were buying solar panels for 74 cents a watt. That has continued to drop. Now it's closer to 45 cents a watt. Racking budgets, inverter budgets have gone down slightly. Racking budgets have gone down slightly. Balance of system cost is about the same. And so what we're calculating is a dollar per watt project budget, so that you should be able to say, okay, if I pay $2.27 a watt for my solar array, what's my payback going to be? Or if I want a 10-year payback, how many dollars per watt can I spend to achieve that as far as budget targeting? You know, the last thing I like doing as an installer is a whole bunch of design work for the customer to say, oh, actually, that's too expensive, too long a payback. And the customer who says, I don't really care about the economics, sometimes you can say, okay, it's going to be a 12-year payback, and they say, fine. And other times they say, 12 years, there's no way I'm going to do it. And so I like talking about payback and project budgets at the very start of the conversation, although some customers, maybe more savvy customers, want to avoid those topics until they get more information. And so how do you calculate simple payback? Well, you take the dollar per watt price. I'm paying $2.50 a watt for my solar array installed by a turnkey installer as part of a professional bid process. Tax credit used to be 70%. For better or worse, it's dropped down. It's now 26%. So this needs to be by 74%. Import tariffs have gone up. The tax credit was only expanded for increases in exports in the natural gas market. Natural gas exports are record breaking. Solar tax credit's dropping down. That's not the worst thing that's wrong with the tax credit, though. Still exists. Going to be around for another year at the 26% level. Then it drops down to 22% for another 2 years. Then it drops down to 10% for businesses and 0% for residential owners. So take that as you will. What that means is next year is a good time for a project. 3 years from now is going to be a really good time for a project. But what I like to do is you take the tax credit, you take the part that is going to be carved out, take the price, take the part that's going to be carved out from the tax credit, and then divide by your PV watts. 1 watt produces 1.3 kilowatt hours in your area, 1.5 in my area. Here we're using 1.4. If I know how many kilowatt hours per watt per year I'm getting, and if I know the effective generation rate of my solar array, and this is really easy if you have net metering. If you're being billed 11 cents a kilowatt hour and the buyback rate is 11 cents a kilowatt hour, your effective generation rate is 11 cents a kilowatt hour. If you're being billed 11 cents a kilowatt hour, but the buyback rate is only 5 cents a kilowatt hour, it becomes more complicated, and you have to do some more robust modeling to figure that out. But if you don't have any outflow issues, if you know exactly what your savings is going to be, if you know exactly what your generation rate is going to be, taking your total price, dividing by the amount of energy produced, and the effective value of that energy will give you your simple payback. And so at $2.50 a watt, at a 74% tax credit, at average solar production, at average electric pricing, assuming net metering, what would we get as our payback? Come on. Let's go. So what we're doing is 251 per watt, and we're taking out the 26% tax credit, and then we're dividing by our production, and we're dividing by an effective rate of 11 cents. So we're getting about a 12-year payback for the typical solar array in the United States as part of a competitively bid process where the project is laid out in a simple manner to facilitate good bidding. 12-year payback, including the tax credit. And that's assuming you have net metering. So if you don't have net metering, then it becomes much more complicated. You know, you need to buy a battery, which doesn't improve the payback for residential in most cases. Sometimes it does. You know, sometimes if the payback is not looking very good, you have to pull up your utility's electric rate and start to see what the options are and start designing the array based on the electric rate and just not off of 100% on-site consumption. You know, or you can look at, doing the project yourself, just with the material cost, you might get quicker payback. Of course, that requires work. And so the problem with solar power is that most customers want paybacks that are under 10 years to actually be a market. And solar gets a little bit of a pass because, it does have a 25-year life. And, if you can get 25-year financing on something that has like a 12-year payback, then the loan payments, even at a average interest rate, are roughly equivalent to the cost savings. I actually don't even like that as a business model. If I'm taking out a 25-year loan, I need to make sure that the savings are greater than the cost savings. So all of that says solar needs a quicker payback. But that payback does become quicker in higher priced electricity markets. So what that is saying is that like anywhere in the country where electricity pricing is above the national average is starting to emerge as a solar market where, what this chart is saying is that, maybe about 10% of the population will go for a solar array at an 8-year payback. And that's pretty awesome. That doesn't even matter what the percent solar is nationally at the utility scale level. This is just like what consumers will buy it at. And so right now we're at maybe 2.5% solar, and the rooftop solar is not even half of that. And so we're only at 1 to 1.5%. The solar prices, if the import tariffs go away with a little bit more maturity in the design build process, we can get that payback to a financeable point where it could come to market on, at least 8% of our rooftops, maybe more, without much controversy. Now, to go to more higher level of solar penetration, that gets into regular energy politics, which are all about subsidies and very political. So what are some other ways to reduce the payback of a solar array? Checking to see if there's a sales tax exemption is a really good one. Maybe 10% of the states have sales tax exemptions. You have to be aware if the meter fee is going to go up. So sometimes utilities, this is the trend, are starting to charge more for solar customers. What's the buyback rate? And not just, the buyback at the end of the month or the end of the year. Some utilities set the buyback rate instantly. The instant you outflow onto the grid. It doesn't matter if at the end of the month you've consumed more than you've generated. If you don't have that specific net metering protection, often utilities will say, we only give you 6 cents a kilowatt hour the instant you outflow onto the grid. And that can very much diminish the value of solar. We talked about the tax credit dropping down. So this is a software called Aurora, And Aurora is mainly a 3D solar design software, and it's a very good one, but they have a interesting time of use metering modeler where you fill out a survey of appliances, and based on your region and based on your month-to-month electric bill, they kind of estimate what your load profile should look like under a normal circumstance. In the interest of time, we're just going to move on from that. But basically, in the wintertime, you have high morning demand because of electric heat, and in summertime, you have high evening demand because of air conditioning. And you can get into variable rate structures, which is, my utility has a terrible solar policy. It's incredibly punishing of the solar consumer, but they have an incredible time of day metering policy. And so, if I wanted to go further and not just use digital controls, I could get a battery, not for my whole house, but just to take me through the off-peak, or rather the peak time. And my utility, the time of day rate is only for 3 hours a day. But for many utilities, the time of use rate is all day long. And so a small solar array that can provide most of the peak energy and then a battery to make up the rest can help you avoid the expensive rate entirely. And then the rest of your home energy is provided at a cut rate. And so I love it when I'm in off-peak times. I can crank the air conditioning. I can, use my electric stovetop, no problem, because I'm getting this discounted electricity. And so a smarter solar design might be one that just focuses on the rate structure to get that payback closer than 12 years. Property value is something to consider as well. Most are disappointed by the amount of value a system will add to the property. There's really only one way to do this, which is to go ask a real estate appraiser for an appraisal, and the real estate appraiser will often say, I don't know how to do this. It's almost not fair. Commercial projects can be financed off the value of the cash flow that they generate, and there are third-party solar lenders who will give you loans that are long-term for solar. But the real estate market, they really want compared based off, how much value will it add to the sales price of the home? And the answer is it's not dollar for dollar. It's less than that. And so, what they're saying is the larger the solar array gets, the less value there is in it. So a small solar array is going to make a home attractive to buy, but a large solar array could actually make the home harder to buy. It could make it so expensive that the new buyer says, I don't qualify for that much. I'm going to go buy a cheaper house. So, I would only be putting into the resale value of a system, maybe $10,000 to $15,000 on a $30,000 system. So, that's another thing, is the buyers of these systems really need to keep in mind that if you're putting a solar array on a house to make it more sellable, maybe a 4 kilowatt microinverter system's the way to go rather than trying to do a complete overhaul. Another pitfall of economic modeling is depreciation. Depreciation is a post-tax consideration. And so if you're modeling depreciation, you also need to model the income tax you have to pay as a business owning solar, because you have a lower electric bill, and so now you have fewer deductions, so now you're more profitable. And so if you're claiming depreciation, you need to make sure you're doing a post-tax analysis. There's a software called Energy Toolbase that does exactly this. It makes, crystal clear with discount rates, with state and local taxes, with electric rate escalators, which are usually not that high. It'll do internal rate of return, net present value, simple payback, and it'll model the depreciation and impacts of the taxes correctly to a degree that'll make a CFO smile. Um, there's another, in the interest of time, because I don't want to keep you extra, I'm going to skip up some of the slides that are kind of self-explanatory by photograph, and you can always email me additional questions. The Desire website is a good one to go to for finding out your policies and standards. Some of this stuff is more towards utility scale, saying that I don't know. Well, what I really want to get to is there's another design approach for demand charges for commercial facilities where the goal is to store just a little bit of power in a battery and only discharge that battery power during peak times. And maybe the solar array is there to recharge the battery and also to provide some peak energy during the day. But some facilities, like this one, their peak energy is at a very specific time at the very beginning of the workday. And, the solar array is really just there to qualify the battery for the tax credit. So, the solar array can be quite small. The battery is a little bit larger. And what this kind of configuration does is because it goes after demand charges and peak demand rates, it can actually generate at above retail value energy. And so the payback can be greater than solar by itself. So commercial solar is going to grow very fast over the next few years because without batteries, the solar by itself has not been able to unlock the cost savings of demand charges. But with batteries, the solar array can do a lot with demand charges and generate even better paybacks than without the batteries themselves. So, I use Energy Toolbase, that commercial modeler, to run these kinds of models. And what is most exciting to me about that is to say, look, there's a big market of solar out there where the paybacks unsubsidized are better than what they ever have been. And we haven't been focused on those markets as an industry. But, the paybacks are under 10 years, and you can even get the community to finance these projects through community solar, where community solar owners are happy with longer term, lower rate of return projects to see projects in their area. And with Halfmoon, we have a class dedicated to that topic called Commercial Solar Peakers. So if you want to learn more on that, that's a good class to go to. Here's a updated project budget for off-grid. What price do batteries add? Although lately I've been moving away from industrial flooded lead acid and into used lithium ion. We have a battery class and off-grid class where we talk about these one-line diagrams and the nuances between battery designs. Unfortunately, we can't get there today. So what I want to leave you with, there's 3 skills for solar, electrical, roofing, and general solar knowledge. In most cases, the installers only have strong skills in one area. And so teamwork and team building can improve workmanship and also drive down costs, division of scope, good project planning. And so that's, we have other classes to kind of guide you further along in that. 6 hours is a long time, but it's not all the time in the world. So if you have additional questions, my email address down here, jrskromer@gmail.com. You can also visit either one of my websites and use the chat widget to get in touch with me. I'm more than happy to answer your questions on into the future. But today we are out of time. So with that, I'll pass it back to Halfmoon.
All right, well, thank you very much, JR, and thank you very much to all the attendees. Again, lots of great questions and great information. We are now finished with the Solar Photovoltaic Project Design and Development Series. Remember, your quiz will be sent to your email here shortly. Once you've successfully completed that quiz, you'll have access to your certificate. If you don't pass the quiz right away, remember you'll be able to retake it until you do receive a passing grade. If you have any questions or issues at all now that the program is over, I want to encourage you to reach out to myself or Halfmoon. The best way to get a hold of me is to go ahead and use one of the emails that was sent out to you, and I'll be more than happy to help any way I can. I want to mention that if you did enjoy this class, JR will be presenting with Halfmoon near the beginning of every month. So feel free to join us once again. We are finished with the series, like I said. On behalf of Halfmoon Education, I want to say thank you to
Andrew,
everyone.
I got one more thing. The quiz questions. Outflow refers to how much solar power flows out onto the grid, and then and that is and the utility scale ground mount market is the largest in the U.S. right now. So outflow flows onto the grid, and utility scale ground mounting, and that's it. So thank you. Sorry about that.
Not a problem. Thanks for filling in all the attendees. And I was just going to say thanks to everyone again, and have a good rest of your day. So hopefully we'll see you soon. See you again sometime. Thanks.